Statistical concepts everyone should know. Statistics for life. I noticed something.
What?
The pagination.
Yes, what?
Are you saying there's 58 pages worth of statistical concepts that everyone should know?
This is just part one.
All right.
But I think it'll be faster than.
I know. I'm just. I have to poke fun somewhere.
I mean, yeah, I would too. I'm sorry for my subtitle. It's a bit stupid, but.
Is there why should someone know these concepts? Or is that self-explanatory?
I tried to explain why you should know the concepts, and I try to keep it more conceptual and applicable to your real life, not just analyzing numbers and data, more how to think about things with statistics as a background.
Okay, so this is not a math lesson. It's more more actionable than that.
Hopefully.
Okay.
This isn't Statistics 101.
Okay.
I couldn't help but put a little bit of math in.
I mean, I assume there would be some math.
Yeah, but it doesn't focus on that, so
okay.
It should be fine.
Interesting. I'm very curious.
Yeah, I'm curious how you will react.
Okay.
All right, let's go. All right, the first thing I want to talk about is metrics. Any statistical metric we hear about, the average of something, the median of something, the whatever. And this section is called neutral metrics. So I want to imply that the metrics are not the problem. It's people's misuse of them and people's misunderstandings that allow them to be misleading.
Mm-hmm.
And I'm going to explain this by a pretty simple example, just that the mean doesn't equal the median or the average. I think the easiest way is just to show the kind of plot of this.
Yeah.
I mean, you're pretty aware of this sort of thing, I think, but
yeah, I mean, yeah.
Yeah, so let's just imagine you're at your local bar and they count up the wealth in the bar for each person. And so this chart is showing on the horizontal axis, the x-axis, the wealth for each person, and the count of the people is the y-axis. So it's just it's called a histogram. So basically, in this bucket of around 57,000, we have 7 people, for example.
Okay.
So, and we can simply take the mean, which is about 60,000, and the median, which is about 59,000. So they're very close in this example.
Mm-hmm.
And that makes sense. There's no problem with this. It's not exactly the same, the mean versus median. So if somebody asks you what the mean is or what the median is, it's about the same in this situation.
I would have thought this is unlikely.
This is simulated, of course. Okay. It's not like I went to my local bar and asked everybody how much they were worth.
Okay. Sorry.
This is just an example. Fake
right.
Data. Okay. But let's say somebody walks in and his name is...
Okay.
I'm sorry. His name is Bilon Gizosberg.
Uh-huh.
And he's worth $150 billion. Now, what does this do to the mean, and what does this do to the median?
Okay.
So there's only one more person in, So that means the median is about the same. It's about 59,000. But the mean now jumps up to like almost 3 billion, which just from one person is, it's crazy. It's just one big outlier.
Yeah.
Okay, so that's the kind of setup of how different they can be from the result of just one person, one outlier. And just as an obvious, I just want to clearly state what the mean is. It's just adding up all the values and dividing by the number of values. And the median is just ordering all the values, and it's the one in the middle. So just so we're all clear on that.
Yeah.
And what I've done here is shown, okay, let's say we have the sample size in the left side of the table. So, and it's 101, 1001. So that one extra person is that $150 billion. And you can see how the difference in the mean versus the median it's really extreme until you get to like 1 million people.
Right. Interesting.
Then it starts to get like, at least somewhat closer. But you really have to get up to like 100 million people for it to be pretty close.
Yeah, I would say even 10 million would be you could still use that data in suggestive ways. Based on if you decide to use the mean or the median. Mm-hmm. So even 10 million isn't. Yeah, okay.
Yeah, and this is exactly what happens in the real world, in quoting real metrics. And so that example was a bit, small. We just had 50 people. And this is a kind of more realistic, even though it is simulated, but it's kind of more realistic so if you look at the chart on the top left, we've got like a base population of about 1 million people. Mm-hmm. So 999,900. And then we have on the top right, that chart is, I'm saying like the ultra rich, which I say is only 100 people, but they have a net worth of like, over 100 million mostly. Mm-hmm. So I've just split these two out like into two charts. Mm-hmm. And then the chart on the bottom is just combining them. And even though you have 1 million people, like 99.99% of the people have an average of, or a mean of about, around 60,000. Yeah. If you combine those two groups, the mean becomes 155,000, which
it's almost triple.
If you say like the average wealth in that 1 million people is 155,000, that's totally skewed by the small 0.01% of the people. All right. And this is just like an example of all of of this kind of metric that can be skewed by these outliers. Mm-hmm. I'm not going to like go through every one, but you can imagine how the average is skewed by the small number of people who have the small number of items that are just really extreme. Yeah. One example that is, I think, kind of interesting is life expectancy, where people always quote that like thousands of years ago, the life expectancy was like 30 years. And that's true on average. But they don't mention that the reason it's so low is because of the high infant mortality. So most people, not most, but like many, many people died when they were like just born or like a year old. Yeah. And that skews the average.
I've seen the statistics. I don't remember the numbers, but if they only consider the people who made it past like the age of 6 or whatever, and then it becomes a lot closer to life expectancy of today.
Yeah, it's still a lot higher, of course, today, but
sure.
It's just good to have this in your mind when you hear those things.
It was a lot more of a reasonable number. Like I don't want to say, but I think it was in the 60s or something like that.
That sounds about right from what I remember too.
Okay.
Maybe 50s, but it's not like 30 or 40. Yeah. It still was a lot lower than currently, but
sure.
Yeah.
But 30 is like unusual for somebody in their 30s to die.
Right. That's the point. Yeah. One of them that I always hear, you always hear the politicians talk about is like GDP and GDP per capita. So I actually do illustrate this in the next slide. And just quickly, it's just gross domestic product, which is this formula, just consumer spending, business investment, government spending, and then net exports. And then GDP per capita is just that sum divided by the number of people, which is basically an average output per person. And this is the US GDP per capita from 1987 to 2029. So it's kind of what is expected in the next few years. But you can see it's gone up a lot.
Yeah.
That's totally clear, and that's true. Like the GDP per capita has gone up. But if you break out the wealth by percentile, you get like a much different view of how well people are doing economically. So you see like the top 1% are just like skyrocketing. Top 10%'s doing, the green line's doing better, over time. But like the bottom 50 to 90th and the bottom half below that is just really barely changed in the last, I guess, 50, 60 years. So that's just something that I think politicians always like, they're like, oh, GDP's going up, we're all doing well,
It might be a tangent because it's not really statistic, but I would say like even as long as like all the groups are going up.
Well, I would say that it really depends on the relative increase. This is going on out in another tangent.
Yeah.
But like this is like talking about the income inequality and stuff.
Sure.
Like it's likely that the more and more disparity between the groups, the more and more friction you have between them, and the less happy, the less well off, the relatively the less wealthy people are doing.
Yeah,
that's just a reflection of maybe not a healthy society.
Sure. But at the same time, you can't expect all the groups to be increasing
at the same rate.
Yeah.
No, but like, where does this end? Where does this go? Like, I don't know.
Sure. All right. But I think
I guess that's not, the point is that politicians will just use this as saying like, we're doing well for the common person when maybe they're just doing well for the top 1%.
I think a good example is Ireland. Their GDP per capita has went insanely high, and sure, their median as well, like wealth per adult, has gone up, and all their life metrics has improved a lot. But if you just look at the GDP per capita, it looks like way, way, way more than all the other European countries, when in reality it's in the same neighborhood, as I understand.
Yeah, it's probably due to the business investment.
They had some tax haven status for big businesses, big tech companies, all of them were registered there.
Yep. Yeah.
But anyway, this is how averages can be used to give a partial picture plus our small tangent.
All right. All this was to say that just a metric is neutral. It's just a number that's calculated in a certain way. And if you don't understand how it's calculated, it can be misused and you can be misled. So you have to know like what goes into the calculation, what are the assumptions that it has within it, and what does the distribution of the data look like there. So the next section I want to talk about is distributions.
Okay.
These are going to be about theoretical distributions. So what we were looking at the histograms, which is it's a kind of distribution. It's more like I would say like a coarse distribution in loose terminology. I'll show you what I mean. But basically, the distributions show you in the data what's typical, what's rare, and what should be extreme, theoretically.
Okay.
And these are, I'm going to be talking about probability distributions, technically, but we'll just call them distributions. So they're just models of where the values are likely to occur. And each distribution has its own properties, usually related to, are they symmetrical? So that means, are they like on the right and left side, is it the same, or is it skewed towards one side, or like bounded at one end? And then the variability of it, like how wide is the distribution or how narrow it is. And then the ends of the distribution, like the extreme outer values, like the top, percent or less even. And this is the same histogram we were looking at before. And we can just add a kind of line on top of that. And that looks more like a distribution now.
Mm-hmm.
And now we make it a smooth distribution. So this is just a visual representation of an actual normal distribution.
Mm-hmm.
And there are tons of distributions, and they're all useful for describing like the structure of data in different situations. These are all continuous distributions. Is this getting too into the weeds?
Well, I had two thoughts, but I don't know if I should interrupt you.
No, go ahead, then I'll get back into it.
First of all, some of these are very similar.
You might think that. But like if you look closely.
I mean, I see it, but it's like playing a game of spot the difference.
Right. And part of it is due to the parameters that you choose for the distribution to show how, wide and narrow it is.
Okay. So these are just like one possible
visual representation. Like the normal distribution, this one looks a bit smushed, but you can spread it out and it's still a normal distribution.
Right.
It's just, having them all on one chart is...
Yeah. Okay.
Yeah.
Got it.
So these are all continuous, meaning it's not like an integer, like a whole number count-based distribution. So there's no...
me.
Let me show you what I mean.
Yeah.
The next category is like called discrete distributions. And those are like where it can be a count, basically. like where it's 1 or 2 or 7, or, it can't be in between those numbers.
Okay.
And those, like Bernoulli is like 1 or 0 or true or false. That's it.
Okay.
And these are all these probably do look a bit more different than the previous ones we were looking at.
Sure.
These 2 slides were just mainly to show like visually what they look like. There's lots more, of course, even than these.
Yeah.
And this is just a list of what they can all be used for. Okay. I think some of the main ones to call out, of course, is the normal one, which is like, you see that everywhere. It's like the bell curve, like height of adults. Everybody knows that one. There's other ones that are kind of pretty well known, binomial, I think. Exponential, maybe. Like the gamut, that's not well known, but like you can model rainfall amounts with that, which is like, it's so strange, but you can model rainfall amounts with this distribution.
Okay.
Just in statistics, we use these distributions to describe the real world data and how the values line up, like where the typical values are, where the rare values are, and the extreme values. Some of them are less realistic. They're mostly just used in, mathematics and stuff, but
right.
Many of them are actual real world things. You want some math?
Sure.
So this is the mathematical equation for one of those distributions. Any idea which one?
Nope.
Okay. So yeah, that's fine. I mean, who knows these? They're pretty complicated looking. And then you have the problem with all the Greek letters that just make people be like, what does this mean?
Yeah.
Yeah. But I will show you, this is actually the equation for the normal distribution.
Okay. That was going to be my guess.
And I just want to show visually a bit like what these terms mean, like, and what they describe. So like this, the mean is just mu there, and that's there. That's just showing where the center is.
Yeah.
This sigma is just showing it's the standard deviations. So how spread out is that distribution?
Right.
And that occurs up here and here because it's part of both of those things. It shapes both of those things, the peak and the spread.
Right.
And the exponential decay is how that comes down from the peak.
Yeah. For this to work, does it have to be like exactly symmetrical?
The normal distribution is symmetrical by definition.
Okay.
Some of those other distributions are not symmetrical, and that will be reflected in the equation. You would see like a bound.
Okay.
On that. And what this is saying, like x is the horizontal axis. So for every x, if we have an x here, we can determine the height of the distribution by this equation. So if you imagine it just going along, you can see how high it should be based on this equation.
Gotcha.
If you just plug in the x. This is a bit simplistic, but I'm just trying to explain intuitively.
So one could use this like as a simplistic explanation to determine whether one's height is, let's say, rare or extreme.
Mm-hmm. Yep. Mm-hmm. Okay. You can, if you know the distribution, if you know the parameters, and you know your height, you can figure out where you are on that and determine, is that 1 standard deviation away from the mean or 2, and that corresponds to like 66% or 97% or 99.7%.
How would you explain being 1 standard deviation away or 2 or whatever?
In the normal distribution, the 1 standard deviation means that if you're within 1 standard deviation of the mean, that's 66% of the values within there.
Okay.
And 2 is 97.5, I think. So if you're above 2, you're in like the 2.5%, somewhere in that outlying.
That means you're taller or shorter than 97% of 0.5% of people.
Mm-hmm.
Okay.
Okay, yeah. And every single distribution has a different equation and different parameters. And you can change the parameters and the distribution looks different. So just to summarize, all these distributions really do is define, like, theoretically what values in the data set are typical and what is rare and extreme based on that distribution. And I like thinking about this conceptually because you can figure out, okay, is this value a likely thing or is it extreme? Does it fall within, the expectations I have? Or is it like a crazy outlier that could be in the distribution? Or maybe I am thinking about the wrong distribution. I've got to...
How do you make that determination? Well, I was going to ask this.
This is more advanced, but there are statistical tests that you can do to see if the data is likely from a distribution where you do get a p-value.
Okay.
So you can do that, yeah.
Okay.
So what these distributions show is a single variable. There are joint ones, but I don't want to go there. Right. But how can we talk about relationships between more than one variable? This will be interesting. So this section is correlation, confounding, causation, and the stories we tell. Mm-hmm. So I think this will be more easier to understand. The distribution, I knew that was going to be a bit more difficult to get through.
I wouldn't say it was difficult, but
maybe less obviously applicable.
Yeah, that.
Yeah, this one I think will be easily applicable to your own life when you're looking at any sort of data analysis. So first we'll talk about correlation. And we've all heard, this variable is correlated with that variable, blah, blah, blah. We all have heard correlation doesn't equal causation. Like that's the catchphrase that is good that people have become aware of, mm-hmm. of course. But I want to go a bit deeper into correlation and what it can show and what it can't. And we're going to be talking about linear correlation here. So I have these 4 data sets, and we just have each data set is just plotted as a scatter plot where on the x-axis you have one value, y-axis the other value, and we just put them together on the chart. And They look pretty different, right?
Than one another?
Yeah. So the data on the top left looks very different from the data set on the bottom left, bottom right, and bottom left. They all look different.
I'm guessing your next slide is the trend line, and they're identical. Ha!
You spoiled the surprise.
Sorry.
Yes. So the correlation and the trend line, the regression line is exactly the same for each of the data sets, and yet they look so different. And this is just an illustration of the problem with just saying something's correlated with something else. Like if you don't show me the data, I don't know if I should take any, real world validity from that correlation. For example, the bottom right one, it's all due to this one outlier. Everything else, there's like clearly no relationship between.
It's the same with or it's similar there.
Similar, a bit less extreme, but yeah.
Yeah.
And then this one is, yeah. And this is actually a well-known statistical teaching data set. It's called Anscombe set. It's just some statistician, I don't remember when, it was like 100 and some years ago, developed these four data sets to show the problems with correlation. And this correlate, like that 0.82 is a high correlation. Remember, 1 is like perfectly correlated. So 0.82 would, if you saw that in a real world data set, you'd be like, wow, that's really highly correlated.
Right. Like if I were to look at these, I would say set 1 and set 3. Mm-hmm. Like I'm just going intuitively. Mm-hmm. Feel like a lot stronger of a case for the line being true.
Yep.
I guess it's because set 4 is just being skewed by one outlier, and set 2, there's a good chance that the thing will end up going down. Mm-hmm. But yeah.
Yeah, no, I agree with that. That's what I'd say as well. This is clearly some, I don't know, parabolic process. These two, definitely there could be some real relationship between the data. This one's 2 is like not a linear relationship. It's a curve. It's
Yeah, but, okay. It's set 2. Okay.
Yeah, 1 and 3, yes, probably
looks more linear.
More like a real relationship. But of course, just because they correlate doesn't necessarily mean anything.
Yeah.
Yeah. All right.
It could be UFO sightings and meat eaters or whatever.
Yeah, that one. Yeah. I don't want to go into this is just, if you are curious about the actual math behind that correlation coefficient, this is what it is. Mm-hmm. And just as a reminder, the correlation coefficient that R is always between -1 and 1, and closer to 1 is more correlated, or -1.
Yeah.
That's just inversely correlated.
Yeah.
Then the question is like, what's a good correlation? What number is good? You want to guess? Like, is 0.6 good? Is 0.3 good? Is 0.9?
Well, it depends on what I'm measuring. But generally, yeah.
My favorite response is it depends on the situation. Yeah. Yeah, okay. So let's talk about confounding.
What is that?
What is that? So we have this chart that has shoe size on the x-axis and reading score. And let's say we make a model, a regression model, so we fit a line through the data where we want to predict the reading score from a person's shoe size. Does this make sense?
Yeah.
Does it make sense, like,
to do that
logically, though?
No.
Right. But when we do the model, we do the regression, we come up with the p-value that indicates that it is a significant predictor, meaning it mathematically is true that the shoe size predicts the reading score.
Right.
Sorry, not true. I shouldn't say true, but like it's.
When I saw this, I would like my first instinct was, is this real data or did you like make it up?
This is simulated.
Okay.
But this is what it would look like, though. Like, imagine this is people under the age of like 18.
Okay.
As their shoe size increases, their reading score will increase.
Right.
So you kind of see where I'm going with this.
Yeah.
So let me show the next chart. So let's say in that same data set we collected, we also have age.
Right.
So now we're going to do the same type of model where we predict the reading score, but from just the age. And again, we get a p-value of less than 0.5, which just means it's significant. So the model says we can predict reading score by age.
Right.
Pretty similar results.
The next thing that I think you would do is control the first thing by age.
Right. And how are we going to do that?
Well, take one age group.
I see where you're going. That is actually a way to do it. Or simply in this situation, we can just put them both in the model. So you just create a model where you have shoe size and age predicting reading score.
Why would you do that?
Because then you can get a separate p-value for the age and for the shoe size. And here, that means that you're taking into account the age when you have shoe size in the model. So it's basically controlling for shoe size.
Right. If I block out the visualization for a moment, what you're telling me is there's some formula, math that you can do to just determine that this variable was a better predictor than the other one.
So I would just want to emphasize the confounding part of this. The confounding part is the reading, the shoe size. That variable appeared like it was significant, like it was predictive, but it was actually age that was the real thing. So once you take into account another variable, you remove that effect, that first initial, thought that it was shoe size.
Right.
And it's actually age. And this is a common problem, like in health studies where they have one variable and they say this causes that, but it's actually that variable is just confounded with a third variable, and it was actually that variable that was the cause and not the initial one.
Yeah.
So that's the idea.
Oh, I had assumed that once we got to the shoe size and age part.
Yeah, okay. I think you got it.
Yeah.
Okay, so I think we got the idea of what confounding is, just variable, one variable being confused with causing something, but it's actually another variable that's really the true cause. Now, let's talk about causation. Mm-hmm. So, just in a statistical sense, we can test if something causes something else, if A causes B. And I think this example will kind of bring it home easily. I want to talk about a randomized controlled trial, which in experimental design is the way we test causation. And let's say we have this research question: does melatonin increase sleep duration? So that means that does melatonin cause sleep to be longer? Mm-hmm. So the way we do this is we'd set up a randomized controlled trial, and that means you would have two groups and you would randomize people. One group gets melatonin, one group does not. And ideally, they don't know what they're getting. Mm-hmm. And that's the control. The control group is used to compare the outcome, the sleep duration, against the treatment group. And we can do just statistical tests to see if that's different. The trial's just applying that intervention. So that's the randomized controlled trial. And this is just a chart of something like you could see in a scientific study where you have the control group here and the treatment group and the sleep duration on the y-axis. And you would, from this, you could say in this population, yes, it appears that melatonin does increase sleep duration. And the point of the randomization is to balance out like any factors that we don't know about.
Yeah.
And if it's randomized and if we have enough people in each group, we should say that maybe whatever factors are present will be balanced in each group. So we can say that the ideal thing is if we can say that we're only changing one thing in the trial, melatonin or not, and everything else, all the other variables about the people are pretty much the same. Mm-hmm. That's the ideal case. Obviously, it's in practice, it's much more messy. So just to say again, these randomized controlled trials can test causality just by randomly assigning subjects to treatment or control groups, applying the intervention, and then comparing the outcomes with statistical tests, of course. Okay. So that's causation.
The only issue I see with your experiment is that you're just measuring sleep duration and not how much their duration changed from before taking it.
Okay, so that is
one of the variables that you...
That is a different type of design, which is also can be valid, but it's just a different way to analyze it. That wouldn't matter in this case.
Because you randomized the...
Because I randomized it and I have enough people that it should equal out.
Okay. Fair enough.
But I mean, good question. There are different types of randomized controlled trials, and that could be a different type. This is very idealistic.
I know. It's never going to look exactly like that.
I'm not explaining any of the statistics behind it, so it's just to show that you can, and we do try to test for causality. Now we get to the stories we can tell about data. So I'm going to show a chart, and I'd like you to kind of describe what's happening and what you can take from it, and maybe, does this look correlated? Does this not look correlated? What do you think? And on the chart, I'm not going to name the variables that you're looking at. It's just going to be variable 1 or variable A, B, C.
Okay.
Okay. And just to explain it a bit more, I'm sorry for the double y-axis. I don't like these because it's always messy, but the red line, the units are on the right side. The purple and black are on the left side.
Okay. So just to be clear, this is not simulated. This is something that is real data, and you want me to...
This is real data. I did not simulate this.
Okay. So the x-axis is obviously year. And is the question whether these three things are correlated?
Tell the story.
Okay. Okay, so I'll go by unit because A and B have the same unit. Mm-hmm. They've both increased over time, but A has had like a more steady increase, whereas B has seen a surge and then continued increasing. I'd say B has increased more sharply from 0 to very high, whatever unit it is, whereas whereas A has increased slightly but steadily, more or less. Yeah.
Mm-hmm. A little, yeah.
C, which is something else entirely based on the unit, has increased with B, or B has followed C, but then C has decreased, whereas B has continued to increase.
So you said B has followed C. That's what you said?
Well, not initially. It is what I said, but like I'm not saying that it's causal. I'm just saying it looks like in general B is like C but delayed by a few years, at least for the middle section of the time period. But then they have inverted. I don't think any of these things are causal.
You might be biased from what we just talked about.
I might be, but at the same time, I really don't think I would have said this is causal because none of them follow the other, like... And even if they did, I might not say that. But in this case, there's clear instances where some of them precede the other and then go the other way around.
Yeah. Okay.
What are we looking at?
I think that was a pretty good analysis. I wouldn't, I don't think anything's totally clear on this chart, especially not knowing what these things are. But I think it's a good exercise just to remove what the variables are and tell a story without knowing what it is. So you want to see what they are. So the red is heart disease deaths in thousands from 1900 to 2020. The purple, that more steady line, is saturated fat in grams per day. The black is vegetable oil in grams per day.
Right.
And that quote I have at the bottom, which says figure 2, which is this figure, correlates saturated fat and total vegetable oil consumption versus heart disease deaths in the USA, with data on all three going back to at least 1909. That is from a scientific study that you can read. It's and their argument was that this data clearly shows that vegetable oil correlates, they don't say causes, but correlates with heart disease deaths. Does that make sense given what you had described before without seeing the variable names? Are you wanting to change your interpretation now? And is that a good idea?
Well, because the conventional wisdom says, because I know some things about what causes heart disease, I am tempted to fit some kind of a story to this. So
it is tempting.
I do feel tempted to be like, well, it was going up but then it went down, but that's because the healthcare improved, but it is very different than just looking at the numbers. It becomes a different exercise.
Mm-hmm. Yeah.
So, I can see how someone could make a case that vegetable oil has been pushing the increase in heart disease, but I don't know whether or not there's any other factors that could be doing that.
Yeah, that definitely is tempting to make that story. I will just point out that it does look like heart disease increases before vegetable oil increases. And then as vegetable oil keeps increasing, heart disease levels, it stops at 73 and then starts going down. So it's not clear what I'm saying. Like it's clear you can't make a clear-cut case that especially from this chart.
Right.
Especially from these large, population-based metrics anyway. You can't, this isn't causal. There's no way you can say that. It can be part of a story, but...
maybe you can use this to set up a randomized control trial.
There you go. Well, I don't know if you'd want to... Yeah, I mean, in an ideal world, yes, that would be the way to go. That might not be practically possible in this,
Sure.
in this case. Yeah, but that's all I wanted to show, how we can tell a story by knowing what the variables are, and the story is probably going to be different than if we didn't know what the variables were and just was looking at the data without knowing what the data meant.
Yeah.
Yeah, and that, I think that's the danger with all of these, with the confounding part and the correlation. It is a dangerous thing to do statistically. There's one other thing that you may not have noticed. This on the secondary y-axis, the red one, that's heart disease deaths in thousands. Can you think of what might be the problem there? Is there a confounding variable?
Yeah, I see it.
Mm-hmm.
And that one is not per population.
left y-axis is grams per capita, so per person.
Yeah. The other one isn't.
The other one is just a raw count.
That's terrible.
But what's happened to the population?
Yeah, that's horrible.
Yeah.
Like, this is an actual thing they used?
This is the exact chart that is in. I have the link to the paper right there. You can look. It's also in a YouTube video that they have.
I believe you. Like, it's just
yeah, insane. It's in there, and that is the label of the chart. Well, it was a good story.
Yeah, I guess.
But yeah, it's definitely
I mean,
not the whole story.
With things like this, I always ask, is it dishonest or did they just make a mistake?
Yeah, I know. I can see them making a mistake, but
I mean, I didn't notice it, but then I didn't make the chart, so
right. You didn't make the chart. You're just looking at it for a minute, like yeah.
If you had told me, like, make this chart, I would have picked per capita.
Yeah, well, I don't, and it's not like that would be easy to calculate. It's not like that would be difficult to calculate.
Right.
Like, you know, you can get the population of the U.S. over the past 100 years, no problem. But maybe it doesn't tell the story as nicely.
Right.
So just to summarize this section, not all the patterns that you see in the data are causal. You know, it especially if you're just looking at a chart of this variable versus that variable, like you can't tell. You have to know how they're produced and under what circumstances and much more details. Like I was saying, correlation could mean nothing, as we saw in some of those previous charts, or it can mean a lot. Mm-hmm. We just don't know. It depends on the situation. It can confuse or obscure those real relationships. We can test causality, but really carefully, like in a really tightly controlled setup, like that randomized controlled trial. And the last thing about the stories, you know, are we just creating stories in our minds that make sense because things seem to correlate together and it backs up the story we want to tell?
Right.
So if these two variables are related, now let's talk about like what pattern is that relationship follow? So, you know, we saw some relationships like in that data set where it looked pretty linear. We saw that one that was curved, that kind of thing. That's what I want to talk about.
Okay.
And it's kind of a shapes of change. And what curve are you on? What point in the curve? So this will be very visual and conceptual. I don't want to get too deep into this one. It's just kind of a quick exercise to look at some shapes of change. Okay, so let's look at this. You have on the x-axis, the horizontal one, you've got any input, whatever you want, and on the y-axis, you have output from that input. Mm-hmm. Don't think too hard, just something. And these curves represent different relationships that input has to the output. So let's say the red curve, you know, if you put in this much input, you get out that much output.
Yeah.
You know, in the gray curve, if you get this much input, you get that much output on the Y.
Yeah.
Which kind of makes sense.
Yeah.
And these four curves are just showing different kinds of relationships. So let's say the output is something good, like which curve do you want to be on?
The red one.
Right.
All else being equal.
Right. If this is all the information you have.
Yeah. Like,
yeah.
If you tell me like the red one costs 100 times more than the gray one, then I choose the gray one. But
no.
Yeah,
same input.
Then the red one.
Right. Okay. So the next chart I'm going to show is the same lines, just farther out in the axis. So we just moved that axis out.
Yeah.
Now, which one do you want to be on?
The red one.
Still?
Yeah.
Not the...
Well, what are the chances that I'm on that? I have that much of the input.
Okay. So you're saying like you're playing it safe. You think you've got more...
Yeah.
More likely to be somewhere over here.
Yeah.
Okay. Let's keep going.
Probably gray one.
So now you're getting up there. Okay.
And yeah, now, I'm just assuming I'm somewhere in the middle.
Rather than assuming one point, assume that this is like you over time. So the input is kind of going over time. Like you start at one point, you start like here, and over time you go this way, and the output is determined by the line.
I'm gonna stick to the gray one because then I'm most of the time higher than most of the others. Does that make sense?
That makes sense. I mean, that's like, you're playing it safe.
And it's like, okay, the blue one is higher, but let's say this is like a lifespan. So what? Like I'm highest the last 5 years of my life. So,
All right, let's keep. I got one more.
Yeah. Now the blue one.
Yeah. So, all I want to say is like, when you're like in the beginnings of some process, it's very difficult to figure out like what line you're on. They might, if you zoom in, like, okay, it's clear, but like if you zoom out, it's not clear where you are. If you have like this endpoint where you're trying to get to in your mind, and if you're on the blue line, it's going to feel like nothing's happening for a long time until all of a sudden, like, it shoots up. And the classic, this is an exponential growth rate. The classic one here is like, compounding interest. It always feels like nothing's happening, and then like 30 years later, you're rich. But I like to think about these things also in like, for example, like skill, like acquiring a skill. Like it can feel like really difficult initially.
Yeah.
And you don't know how things are going, and then all of a sudden like something happens and like you just start jumping up really fast.
Isn't that more of an S curve though? Because then you kind of plateau.
That could be, yeah, definitely, probably is a plateau, yeah. And then it becomes harder and harder to get better.
Sure, but I see your point.
But yeah, getting to that point where you start like going up is difficult.
Yeah.
Okay, that's all I wanted. I wanted to like, just show this way of thinking about things, not to go too deep. So just a summary, just depending on the context, the changes to the inputs and the outputs can be very different. And if you can kind of think about what shape that it might take, you can say, okay, I feel really frustrated now, nothing's happening, but maybe I'm on that exponential curve and I just need to keep going, and, it'll just eventually just snowball. So if you have an expectation that you're on like, a linear curve, but you're actually on that exponential, you might become frustrated for a long time until you actually see it. And that expectation, of course, can shape, the way you interpret any new data, like new output from that input. which brings us to expectations and reality, or bias. This is the last section.
Okay.
So, I want to go through the first part pretty quickly because there's too much math in it, and I'm sorry. But basically, in statistics, bias is just like a systematic difference between what you expect the value should be and the true value.
Mm-hmm.
And it leads to this bias. And it's like a difference between, like, maybe there's something wrong in the way you measure something, and that incorrectness in the measurement is reflected in every single measurement. So you bias like all of the values, like maybe less than they should be. Does that make sense?
I'm not sure yet, but continue and I will let you know.
Okay. It just means that you're consistently off the truth because of how you're, measuring something or thinking or the sampling of the data.
Oh, and you don't know it. So you're saying, like, in statistics, bias could be not necessarily with your mentality, let's say, but with how you've set up your experiment or measurement.
Mm-hmm.
Okay, got it.
Yeah, and very simple illustration.
Right.
This thing is biased. Like the true value is here. If it's biased and you get this, it's
most useless chart I've ever seen.
Fine. Here's the math. So,
okay.
This is the expectation of a parameter, and it's biased because it's not on the true value of that of that parameter.
Mm-hmm.
Sorry, this was a biased estimator. This is the true value, the parameter that you're trying to estimate. And if you're off, it's a biased estimator. If it's the same thing, just adding a bit of math.
Right.
We'll ignore that. Okay, there's lots of type of biases. I just listed some. I don't want to talk about specific ones too much. I'm sure you've seen lots of these.
Mm-hmm.
Just one of the ones we saw before was like this omitted variable bias, which is kind of like confounding, where you make the analysis, but you've omitted that one variable that was actually the important one. Another one that's kind of interesting is the publication bias, where only positive results from experiments get published.
Right.
Usually the negative ones that say, oh, there's no effect, that usually doesn't get published because it's not as exciting.
Interesting, yeah.
And that's a true thing. Like, that's totally true. Yeah. But they all have the same principle, that they just push the result away from the truth in a systematic way. And this bias can be self-reinforcing in a loop. And this is my nice diagram of how that happens. So you start with your current bias, which maybe is a little bit.
Right.
Then you selectively look at things, perhaps videos, whatever.
Right.
You selectively your attention's grabbed by that video. Then you selectively search for evidence to back up that bias. Then you reinforce that current bias. Then that reinforced bias, which is increased, now becomes your current bias. And then that causes you to be even more selective in your attention. And, it's just this loop that can get ever more extreme.
Yeah.
Don't you love my self-reinforcing feedback loop of bias?
It's more informative than the chart you had earlier.
That's true. That is true. All right. Then you'll love this next chart. which is basically the consequence of that self-reinforcing feedback loop of bias. So this is what I've called the bias escalation curve in conceptually. So on the the x-axis, this is very loose terminology. The x-axis is just the time or the cycles of that reinforcement, and the y-axis is just bias, like just.
And is it going to exponentially increase?
Watch, I got an animation.
Wow.
So, as you can see, because it's a feedback loop, so it's like a snowball effect.
Yeah.
It does over time have this kind of compounding exponential effect. So, to illustrate this concept even more, I've created another chart which has some labels on this feedback loop bias escalation curve chart. And this is the carnivore edition of the bias escalation curve. You might need to zoom in here, but
no, I can see it.
You start on the left. Maybe you have some slight bias, and TikTok knows it, and they show you this video that says meat is a superfood, and you're like, ooh, that makes sense. And then you get showed this video that is titled "Plants Are Trying to Kill You." Sounds familiar. And you spend an hour watching this video with lots of scientific references. And you are convinced like this story makes total sense, and you start only looking at carnivore sources of carnivore influencer type sources. You're becoming more and more biased. You're going up the escalation curve. Now you're like, oh, now you get into the kind of conspiracy part where you're like, fiber's an industry scam. Like you don't need it. It doesn't make any sense. Any counter evidence is just a conspiracy. Then you get, oh, humans are naturally biologically carnivores, and you end up eating only raw organs at the top of the bias curve. Now, you might start to think that I'm biased, which everybody's biased. So I made a vegan edition
sure.
of the bias escalation curve, which is basically a mirror of the same thing. Where you start out, you see a TikTok that says plants are superfoods. Then there's a video, you see it's meat rots in your colon. True video, though. It's out there.
Is it?
Then you start only trusting vegan sources. You start thinking about it's conspiracy, like protein deficiency, that's a scam, like you don't need much, you get enough from plants. Any counter evidence is a conspiracy. Humans are naturally vegans biologically. It's clear, it's obvious. And you end up eating only raw fruit. It's only fallen from the trees.
I've been on like both of these red lines at some point in my life.
I know. Me too. Yeah. Well, I didn't get too far I didn't get to the raw fruit or raw.
No, organs. I never got to the end of either.
Yeah. But and notice I'm not saying you can be biased and just by chance be biased towards the truth.
Yeah.
Without knowing it, I'm not saying that one of these is right and wrong.
Right. I'll go further that the truth may not necessarily be in the middle.
Right. For sure.
It often isn't.
Right.
It can be somewhere in the middle, but
or parts of one and parts of the other. Yeah,
sure. It's not always dead center.
For sure. No. I'm not advocating for like the truth is in the middle.
Yeah.
No, definitely not.
Because I see this online a lot whether it's with politics or diet or a lot of times with politics, it's like this side is saying this and that side is saying that, but the truth is somewhere right. Maybe, but maybe also
sometimes it is, sometimes it's not. Yeah. So this was just, trying to illustrate how this can happen. And just to wrap up, just that bias is, it shapes our attention and interpretation of data and even how we remember things. And it makes us favor evidence that confirms what we already believe. Like with the story, you tell the story of that chart, like what you believe is going to come out in that interpretation of the data. And it can be this, feedback loop. And I would just say, it can gradually come up where you don't even realize it.
Yeah.
Slowly and slowly. And because it's kind of, at least I like to think of it as a, exponential growth. Before you know it, you can get to this extreme viewpoint.
Yeah. I mean, obviously people who are on that extreme don't think that they're on.
Right. Yeah. So I just say, like, maybe from time to time, ask where, am I on this this curve?
Yeah.
If I am, like, where would I be on it? Like,
Have you seen this experiment where they showed people some numbers, whether or not this cream cured this rash, and then they asked a bunch of random people, and then they changed the question. So they asked people if it was causal, whether the cream was curing the rash or not.
Right.
And they got a certain set of answers. And then they changed the question.
Like slightly different wording or something?
No. So it was actually like the numbers, let's say, from gun violence or something. They changed it to something political. And then all of a sudden, people's answers kind of fit their stories.
Right. Like, well, it depends on...
even when they changed the numbers to be the other way around, both sides did this. It wasn't just gun, it was also climate change. It was a bunch of different stuff, and it seems like people just gravitate towards making it fit with their preconceived.
I think the only way to remedy it really is to just try to be aware of it, of your own biases, because everybody has them.
Yeah.
All right, that is my part one of statistics, statistical concepts that everybody should be aware of.